This is day 6 of Chapter 8, the beginning notes for Section 8.3. Section 8.3 is all about the sample mean, where the previous section, 8.2, was in reference to sample proportions. Let's refresh our memories. What is the formula for the standard deviation of the sampling distribution for a sample mean? That would be the standard deviation of the population divided by the square root of n. The issue we have with this formula is that if you are trying to predict the population mean, it's very unlikely that we would actually know sigma, the population standard deviation. So we must estimate the population standard deviation by using the standard deviation of our sample, which is S. The issue this causes is that S, the standard deviation of your sample, it could be small, it could be large, and that is because of sampling variability. If S happens to be quite small, then the confidence interval will not be large enough to capture your true proportion, and it won't capture it often enough based on the confidence level that you had chosen. And this is especially the case for small sample sizes. Remember, smaller sample sizes mean you do have increased variability. So a small sample size is more likely to have an extreme case in either direction, to where you could have a very large standard deviation or small standard deviation. And when that standard deviation happens to be small, you might end up with a confidence interval that is way too narrow. So to help fix this, we introduce what we call t-distributions. You need t-distributions and t-scores when you don't know the population standard deviation, and we use those instead of normal distributions. The t-distributions are always going to be different depending on what the degrees of freedom are, and the degree of freedom is always just one less than the sample size. So here we have n minus 1. That's how we find the df. So look at these three pictures here. When the degree of freedom is infinity, this is actually the standard normal curve. When the degree of freedom is small, like 3, we see a lot more area in the tails and a lot less area in the center of the distribution. And as that degree of freedom increases to 6, to 10, to 100, you will approach the standard normal curve both in the center and in the tails. So the reason why we look at t-distributions like this is that in order to include 95% of the standard normal curve, you only have to go out 1.96 standard deviations in each direction. But if your degree of freedom is 6 or 3, you are more likely to get extreme results in either direction. So in order to guarantee that your confidence interval captures the true value, you need to include more standard deviations, like 2.45 or 3.18 in each direction. The more standard deviations you're including, the more likely you are to capture that true population standard deviation and ensure that your confidence level is met. So how do we calculate which value of t star to use? First, you identify your sample size, n, and you find your degree of freedom. Then you go to the appropriate row and column. Here are your rows for degree of freedom. Here's the column that pertains to your confidence level, and you find your t star. So everything inside of this table are all t stars. Remember, when it's infinity, if the degree of freedom is infinity, that is the standard normal curve. These are actually z stars, this very bottom row. Or you can find your t star using technology, especially if your confidence level needed is not listed in table B. So you are going to use the inverse t command on your TI Inspire. So open up your TI Inspire. You're going to click Menu, go down to Statistics and Distributions, because we are trying to find a t-score. And so you're going to go up to inverse t. A lot like inverse normal, to find z star, we're going to do inverse t. And here it's asking for your area to the left and your degrees of freedom. To find the area to the left of the curve, sketch your distribution and label the confidence interval needed or the confidence level needed. So in my example, say we needed 94% confidence. That leaves us 3% or 3% area on each side. So what are the t-scores that are here and here? Or so that means the area to the left would have to be either 0.03 and you would get a negative t-score, or we're looking at area to the left of 0.97, and that would give you your positive t-score. But both should give you the exact same number. So just use the positive using 0.03 or just use 0.97, either way. And then in this case, the degree of freedom is just one less whatever the sample size was in that problem. So example one, suppose you wanted to construct a 90% confidence interval for mean mu of a population based on an SRS of size 10. So our 90% confidence interval puts us in the 90% column, and an SRS of size 10 means our degree of freedom is 10 minus 1, which is 9. So you go to row 9, and we get our z-score to be, our t-star, to be 1.833. Part B of this example says 99%, but let's change that to 90 because the table that I took a screenshot of here, I didn't include the 99%. So let's just use the 90%. That puts us in this column, and our sample size is 75. So if we do n of 75, subtract 1, we get a degree of freedom of 74, and we are somewhere between 60 and 80. So that's going to give us these two t-scores. 0.671 and 1.664. Now, if this is the case, you need to go conservative here. So the whole reason we have to be conservative is we want to make sure that we are meeting that confidence level. We want to be 90% confident that we are going to capture that true mean. So you're going to use the larger t-score, and that will ensure your confidence interval is wide enough. We want the t-star to be 1.671 in this example. The other thing you could do here is use technology, and that would give you a more accurate t-star that would be a little bit more specific. It would be a t-star somewhere between those two decimal values. Let's take a look at our conditions for constructing a confidence interval for a population mean. Remember, the population mean is mu, and we are trying to predict what that is using some x-bar. So you're going to take a sample, and you're going to try and use that to create some sort of interval to capture what the true population mean is. So in order to do that, you must check your random condition, means your survey or experiment or whatever is going on in that problem, that it was random. And I usually just pull the sentence straight out of the problem. Pull that sentence that states that it was randomly selected directly from the question. Don't waste any time trying to reword it. Just pull exactly what that says out. Save yourself time because that's the easy one. Next would be the independence condition. The independence condition is also known as your 10% condition. This is very important when you're sampling without replacement because you need to make sure you're not sampling too much of that population. So you want your sample size n to be less than or equal to 1/10 the population size. The third condition is the normality condition. For sample proportions, the normality condition is the large counts rule. That's n times p, and that must be greater than or equal to 10. But in this problem, when we're predicting the sample mean, we don't have any p-value. There is no sample proportion or any sort. So we just need to make sure we have a large enough sample, and that sample needs to be larger than 30 or equal to 30. And if that is the case, the central limit theorem applies, and we meet the normality condition. If the large sample is not the case and you have a small sample, something that's less than 30, then you must have a parent population that is already normal, and then you would be okay. And if that's not the case, And often you won't even know the distribution of the parent population, especially when you're trying to predict what the population mean is. So what you're going to have to do, or what you're allowed to do, is graph the distribution of your sample data. If the distribution, add in the word the here, if the distribution of sample data is roughly symmetric without any outliers, then you can assume that it's normal, or that it came from a normal population. So that would be the normality condition for estimating the sample mean mu. Either you have a large enough sample and the central limit theorem applies, or the parent population is already normal, or if you have too small of a sample and you don't know the shape of the parent population, take a look at your distribution of sample data. If it's roughly symmetric, doesn't have any outliers, we can assume it came from a normal population. So what is the formula for standard error of the sample mean? It's similar to the standard deviation of the sample mean, but instead of using the population standard deviation, you use the standard deviation of the sample. So remember, S is the standard deviation of the sample. And when interpreting this value, the standard error of x bar, the standard error of your sample mean, it describes how far the x bar will typically vary from the mean, and it's only going to work for repeated samples of that same size, whatever that size n is, because this standard error will change based on your sample size. So that is important to include in your interpretation for what the standard error is. This formula is unfortunately not on the formula sheet, nor is the formula for the confidence interval for the population mean. What is on the AP formula sheet is this formula here. It says statistic plus or minus the critical value times the standard deviation of the statistic. And so that's the general confidence interval formula that you're going to have to use this to apply it to both proportions and means. So if it was for proportions, we would have our p hat, our z star, and then the standard error for formula. But for sample means, you have x bar, because that's your statistic. Your critical value is now t star based on whatever your degree of freedom is. And then you have the standard error of the sample mean of that statistic. Remember, t star has degree freedom of n minus 1. And that is all for these notes. I'll catch you in class.